In our previous module 5, we have learned about Putzer's method to calculate e to the power at. We have also learned an alternate way of calculating e to the power at in some special cases. In this module 6, we will learn about power series method, and also we will learn about the variation of parameter method for non-homogeneous cases. In this module, we will learn about the power series method. We consider a homogeneous linear system of the form x dash t, which is equal to dx dt, which is equal to at x t, with initial condition x 0 is equal to b, given by equation 1, in which the given n cross n matrix At has a power series expansion in T and convergent in some open interval containing the origin. For example, let At may have the form A0 plus T A1 plus T square A2 plus dot dot T to the power k AK plus 0 0 for norm T less than R1, where the coefficients A0, A1 dot 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 are given n cross n matrices. We try to find a power series solution of the form x t is equal to B0 plus T B1 plus T square B2 plus dot dot plus T to the power k Bk plus dot dot with vector coefficients B0, B1 dot dot dot. Since x 0 is equal to B 0, we may take B 0 to be capital B. To find the remaining coefficients, we substitute the power series for x t in the differential equation and equate the coefficients of like powers of t to obtain the following system of equations. B1 is equal to A0 B, k plus 1 B k plus 1 is equal to summation r equal to 0 to k A r B k minus r for k equal to 1 2 dot dot dot, which is given by equation 2, which provides the unknown coefficients B I for I equal to 1 2 dot dot dot. If the resulting power series for x t converges in some interval norm t less than R2, then x t will be a solution of the initial value problem 1 in the interval norm t less than R, where R equal to minimum of R1 comma R2. For example, if At is a constant matrix A, then A0 is equal to A and Ak is equal to 0 for all k greater or equal to 1, and the system of equations in 2 gives the following: B1 is equal to AB, k plus 1 Bk plus 1 is equal to Abk for k greater or equal to 1. On solving these equations, we get Bk is equal to 1 by k factorial a to the power k b for k greater or equal to 1. Therefore, the series solution in this case becomes x t is equal to b plus k equal to 1 to infinity t to the power k by k factorial a to the power k b, which is equal to e to the power a t into b, which provides the same result for homogeneous linear system with constant coefficients. We have started this module with a brief discussion on the power series method. We will now look into the variation of parameter for the non-homogeneous equations. We now look into the method of variation of parameters for non-homogeneous equations. Let us consider the non-homogeneous equation of the form dx dt or x dot is equal to atx plus ft. Once we have solution for the homogeneous equation x dot equal to at into x, we can use the variation of parameter method to find the solution of the initial value problem x dot or dx dt is equal to atx plus ft with initial condition x t0 equal to x0 given by equation 4. Let x1t, x2t dot dot xnt be n linearly independent solution of the homogeneous equation given by 3. Since the general solution of 3 is C1 x1t, C2 x2t dot dot Cn xnt, we may assume that a solution of 4 is given in the form xt is equal to u1 x1t, u2 x2t dot dot un xnt given by equation 5. This equation can be written in the matrix form xt is equal to capital Xt into ut, where capital Xt is equal to x1t, x2t dot dot xnt and ut is equal to u1t, u2t dot dot unt, the n cross 1 column vector. Putting the value of xt into the differential equation, x dot is equal to at into x plus ft, and integrating between t0 and t, we get small xt is equal to capital Xt into x inverse t0 into x0 plus capital Xt integration t0 to t x inverse s f s ds given by equation number 6. Since for autonomous case a fundamental metric solution can be given as e to the power at, then equation number 6 can be written as xt is equal to e to the power a t minus t0 into x0 plus integration t0 to t e to the power a t minus s f s ds given by equation number 7. We now look into an example where we solve the initial value problem dx dt, which is x dot is equal to ax plus ft, where A is the matrix 1 0 0 2 1 minus 2 3 2 1 and ft is given by 0 0 e to the power t cos 2t, with the initial condition x 0 is equal to 0 1 1. We first calculate the eigenvalue of the matrix A, and by definition the eigenvalue is obtained from the characteristic equation, that is determinant of A minus lambda I is equal to 0. And if you do that, you will get 1 minus lambda 0 0, 2 1 minus lambda minus 2, 3 2 1 minus lambda, and determinant of that is equal to 0, which is given here. Therefore, the characteristic equation of A is given by the expansion of the determinant, and which we get as 1 minus lambda into 1 minus lambda square plus 4 is equal to 0. If you solve this equation, the first value you get lambda equal to 1 from here, and the second equation gives 1 minus lambda whole square plus 4 equal to 0. And if you take 4 to the right hand side, this can be written as minus 4, and which can be written as 4i square, and hence 1 minus lambda whole square is equal to plus minus 2i, which gives lambda is equal to 1 plus minus 2i, and hence you get the eigenvalues to be lambda equal to 1 and lambda equal to 1 plus minus 2i. Next, we need to find the eigenvectors corresponding to the eigenvalues lambda equal to 1 and lambda equal to 1 plus minus 2i. For lambda equal to 1, we get the eigenvectors in the form x1, y1, z1, where this vector has to be a non-zero vector, and it is obtained from the equation A minus lambda I into some V is equal to the null matrix, where lambda is the corresponding eigenvector. And if you substitute the value of lambda equal to 1 in that particular equation, you will get 1 minus 1 0 0, 2 into 1 minus 1 minus 2, 3 2 1 minus 1 into the eigenvector, which is the components of which are x1, y1, z1 is equal to the null matrix 0 0 0. Now, if you solve this, you will get from the first equation, it is 0 x1 plus 0 y1 plus 0 z1 equal to 0, then 2 x1 plus 0 y1 minus 2 z1 equal to 0, and 3 x1 into 2 y1 into 0 z1 is equal to 0. Now, we are not looking into the trivial solution, that is, we are not looking when x1, y1, z1 will all be equal to 0. We are looking for some non-zero values of x1, y1, z1 such that the vector is a non-zero vector, and hence on solving by attributing some values of x1, y1, z1 which will satisfy these three equations, we can get x1 equal to 2, y1 equal to minus 3 and z1 equal to 2. Please note, corresponding to lambda equal to 1, the values of x1, y1, z1 are not unique. So, for lambda equal to 1, which is the unique eigenvalue, you may get different eigenvectors and you can proceed with any one of them. And hence, our solution x1t is equal to e to the power t multiplied by 2 minus 3 2. Next, we find the eigenvectors corresponding to lambda equal to 1 plus 2i. Proceeding in the similar fashion, we will get 1 minus 1 plus 2i 0 0, 2 1 minus 1 plus 2i minus 2, 3 2 1 minus 1 plus 2i x2 y2 z2 equal to the null matrix. Again, solving in the similar manner, we will get x2 equal to 0, y2 equal to I, z2 equal to 1. And once again, we point out that for lambda equal to 1 plus 2i, the unique eigenvalue, the eigenvector is not unique. You can choose any values of x2, y2, z2 satisfying the above equation. Hence, the solution in this case x2t is equal to e to the power 1 plus 2i into t multiplied by 0 I 1. Now, e to the power 1 plus 2i into t multiplied by 0 I 1 can be written in the form e to the power t into cos t plus I sin 2t. This is just an expansion of e to the power I theta, which is cos theta plus I sin theta multiplied by 0 0 1 plus I times 0 1 0. And if you simplify, you will get it in the form e to the power t multiplied by cos 2t into 0 0 1 minus sin 2t into 0 1 0 plus I times sin 2t 0 0 1 plus I times cos 2t 0 1 0. Separating as a imaginary and the real part, we will get this is equal to e to the power t into 0 minus sin 2t cos 2t plus I times e to the power t 0 cos 2t sin 2t. And therefore, our second solution x2t can be written as e to the power t multiplied by 0 cos 2t sin 2t, and x 3t is equal to e to the power t 0 sin 2t minus cos 2t. And hence, a fundamental metric solution of x dot equal to a x may be given as capital X t is equal to 2 e to the power t 0 0 minus 3 e to the power t e to the power t cos 2t e to the power t sin 2t, 2 e to the power t e to the power t sin 2t minus e to the power t cos 2t. Here x 0 is equal to 2 0 0 minus 3 1 0 2 0 minus 1. Please note, you can easily calculate this x 0 by putting t equal to 0 in this matrix, and if you do that you will get this result. And also it can be easily seen that determinant of x 0 is equal to minus 2, which is not equal to 0, and hence we can calculate the inverse of x 0, which is equal to x inverse 0 equal to half 0 0 3 by 2 1 0 and 1 0 minus 1. Therefore, e to the power a t is equal to x t into x 0 inverse, and if you substitute these two matrices and multiply, you will get e to the power t 1 0 0 minus 3 by 2 plus 3 by 2 cos 2t plus sin 2t, cos 2t minus sin 2t, 1 plus 3 by 2 sin 2t minus cos 2t, sin 2t cos 2t. And consequently, x t is written as e to the power a t 0 1 1 plus e to the power a t integration 0 to t e to the power minus s multiplied by the matrix 1 0 0 minus 3 by 2 plus 3 by 2 cos 2s plus sin 2s, cos 2s minus sin 2s, 1 plus 3 by 2 sin 2s minus cos 2s, sin 2s cos 2s multiplied by the column matrix 0 0 e to the power t cos 2s ds. And hence, after simplification we get x t is equal to e to the power t multiplied by the matrix 0 cos 2t minus 1 plus half sin 2t, 1 plus half cos 2t plus 5 by 4 sin 2t. In our next example, we solve the initial value problem dx dt or x dot is equal to 1 0 0 2 x plus sin a t cos b t, where the matrix A here is 1 0 0 2 and f t is equal to sin a t cos b t with the initial condition x 0 is equal to 0 1. Like before, we have to calculate the eigenvalue of the matrix A, which is given by the determinant A minus lambda I is equal to 0, where lambda is your eigenvalue. And if you do that here, you will get 1 minus lambda 0 0 2 minus lambda, and this can be easily expanded and solved, and we get the characteristic equation as 1 minus lambda 2 minus lambda equal to 0, giving lambda equal to 1 and lambda equal to 2. Next, we calculate the eigenvectors corresponding to lambda equal to 1 and corresponding to lambda equal to 2. As explained before, the eigenvector is obtained from the equation A minus lambda I into some vector is equal to the null matrix, where we have to find the vector which is non-zero, and in this case we have taken that to be x1 y1. For lambda equal to 1, A minus lambda I will give 1 minus 1 0 0 2 minus 1 into x1 y1 equal to 0 0. Now, if you solve this, you will get two equations, which is 0 into x1 plus 0 into y1 equal to 0 and 0 into x1 plus y1 equal to 0. From the last equation, we get y1 is equal to 0, but we cannot conclude anything about x1. So, we take any arbitrary value of x1 which will satisfy this equation. Hence, our required eigenvector will be x1 y1, which is 1 0. Please note, this y1 will always be equal to 0 and x1 you can choose any real number and it is going to satisfy the above equation. In the similar manner, the eigenvector for lambda equal to 2, we will get 1 minus 2 0 0 2 minus 2 x2 y2 equal to 0 0. So, here if we expand this, we will get minus x2 plus y2 equal to 0 and 0 x2 plus 0 y2 equal to 0. So, from the first equation, minus x2 equal to 0 implies x2 is equal to 0 and hence x2 will always be equal to 0 and we cannot conclude anything about y2. So, we take any arbitrary value of y2. In this case, we have chosen y2 equal to 1, you could have chosen any value. Therefore, a fundamental metric solution of x dot equal to ax may be given as xt is equal to e to the power t 0 0 e to the power 2t. And hence, next we compute x 0, which is 1 0 0 1 and its inverse, which is x inverse 0, which remains the same 1 0 0 1, and therefore, e to the power at is equal to e to the power t 0 0 e to the power 2t. And consequently, xt will be given by xt is equal to e to the power at 0 1 plus e to the power at integration 0 to t into the matrix e to the power minus s 0 0 e to the power minus 2s sin as cos bs ds, which is equal to e to the power at multiplied by 0 1 matrix plus e to the power at integration 0 to t the matrix e to the power minus s sin as e to the power minus 2s cos bs ds, and which if we integrate, we will get this is equal to e to the power at 0 1 matrix plus e to the power at into the matrix e to the power minus s divided by 1 plus a square into minus sin as minus a cos as and e to the power minus 2s divided by 4 plus b square multiplied by minus 2 cos bs plus b sin bs from 0 to t. And please note, when you integrate this, we use the formula e to the power as cos bs ds. And this can be simplified and written in the form 0 e to the power 2t plus the matrix e to the power t 0 0 e to the power 2t multiplied by the matrix e to the power minus t divided by 1 plus a square into minus sin at minus a cos at plus a divided by 1 plus a square and e to the power minus 2t divided by 4 plus b square into minus 2 cos bt plus b sin bt plus 2 divided by 4 plus b square. This is equal to 0 e to the power 2t plus 1 by 1 plus a square into minus sin at minus a cos at plus a e to the power t by 1 plus a square and 1 by 4 plus b square into minus 2 cos bt plus b sin bt plus 2 e to the power 2t by 4 plus b square, which can be further simplified and can be written as in the matrix form 1 by 1 plus a square into a e to the power t minus sin a t plus a cos a t and 1 by 4 plus b square into 6 plus b square e to the power 2 t plus minus 2 cos b t plus b sin b t. Summing up, in this chapter, which has 6 modules, we have started with some basic definitions, which includes autonomous system, non-autonomous system, homogeneous and non-homogeneous equation, and then we move into the fundamental metric solution. We have also learned how to calculate e to the power at, and finally we ended our module with variation of parameter for non-homogeneous cases. I hope it is clear to you. Thank you.